3-Eye Atlas is back in the spotlight, but this time, the surprise is in its brightness. A hidden heartbeat captured by a NASA space telescope that normally hunts exoplanets, not comets. In this video, we'll decode what that special tracking run actually recorded, how scientists can turn a simple flicker into clues about 3-Eye Atlas's spin and behavior, and why the time-lapse suddenly jumps in the middle for a very real reason. This observation wasn't a casual snapshot. NASA scheduled a dedicated run to keep 3-Eye Atlas in view from January 15th to January 22nd, 2026, using the same kind of steady, repeat imaging normally reserved for hunting subtle signals in starlight. That choice matters because spin clues don't show up in one pretty frame. They show up in patterns that only appear when you watch for hours and days. So this story starts with commitment, not coincidence. What the spacecraft captured looks simple at first, a bright streak sliding across a dense field of stars with a faint tail trailing behind it. But that simple streak is the advantage. When a target moves through a crowded background, you can't trust your eyes. You have to trust calibration, repeated frames, and careful subtraction of everything that isn't the comet. The reward is a clean timeline of how 3-Eye Atlas changes in brightness as it travels. Exactly the kind of timeline you need to infer rotation and activity without guessing. Then the plot twist hits, and it's the kind you can't script. On January 15th, the spacecraft entered safe mode and paused science operations until January 18th. In the final compiled sequence, the comet doesn't smoothly glide. There's a jump. That jump isn't editing flare. It's the spacecraft protecting itself after an issue tied to a pointing maneuver and its solar panels. Later, MIT researcher Daniel Muthakrishna assembled the usable frames into a time-lapse you can actually feel because you're watching real data behave like a story. That visualization isn't just for sharing, it's a reality check. If the comet's track, shape, and the star field behavior look stable, analysts gain confidence that the brightness they measure truly belongs to 3-Eye Atlas, not star spillover, not pointing jitter, not some sneaky artifact that could fake a spin signal. In other words, the movie helps validate the math. Even with the gap, the dataset still spans multiple nights. That means the next step isn't imagine what happened, it's measure what repeats. Either way, the clock starts. The smartest part of this campaign is that it treats brightness like a code. As 3-Eye Atlas rotates, different surfaces and jets can face the sun and then turn away, creating a rise and fall rhythm in the measured light. That rhythm is what scientists hunt for, a repeating pattern that points to a rotation period, even when the nucleus is far too small to resolve as a solid disk. If you can pin down that rhythm, you've learned something physical from something that looks like a smear. The hard part is that comets cheat. What you measure isn't just the solid nucleus, it's also the glowing coma and dust, which can swell, fade, and blur the signal. So analysts don't treat every brightening as spin. They look for consistency across many frames, and they compare short-term wiggles to longer-term changes in activity. A true rotation signature tends to repeat with a recognizable cadence. A sudden activity spike usually doesn't. That distinction is where science lives. This is where an exoplanet hunting skill set becomes a comet superpower. The instrument was built to detect tiny brightness changes over time by collecting lots of steady exposures. For 3-Eye Atlas, the observing plan keeps the comet's path controlled on the detector, so the same region of pixels is used again and again as it moves. That consistency matters because it makes it easier to correct the starry background and isolate the comet's contribution frame after frame without constantly changing the ruler you're measuring with. Once you isolate the comet's light, you build a light curve, brightness versus time. Then you test it like a musician tests a beat. Do peaks recur at regular intervals? Does the pattern survive after you remove background contamination? Does it persist across different chunks of the run, including the stretch after the safe mode interruption we talked about? Those checks don't make the answer flashy, but they make it believable, because you're not just spotting a pattern, you're proving it's not a trick. There's also a practical reason this matters right now. Around the time of these observations, reports put 3I Atlas around 11th magnitude, within reach of many telescopes, but still faint enough that precision matters. A high-quality space-based light curve becomes a reference line for everyone else. It helps observers time follow-ups, notice shifts in activity, and spot whether the flicker looks periodic or chaotic. Coordinate follow-up, and the comet starts giving clearer answers sooner. The biggest new finding here isn't only that 3I Atlas was tracked, it's that tracking became shareable science. NASA says the dedicated January observations are publicly available through the Mikulski Archive for Space Telescopes. That means anyone can pull the same frames and test the same spin and activity claims. And once you open the doors like that, discovery speeds up. Instead of one team acting as the gatekeeper, the whole community can compete, replicate, and improve the analysis in parallel. And the archive angle goes deeper. The mission's wide field of view had already captured 3I Atlas months earlier, in May 2025, before anyone recognized it as an interstellar visitor. Astronomers only found that pre-discovery appearance by going back through older frames, stacking exposures, and tracking a faint motion across a busy background. That's not trivia. It means the comet may have a hidden prologue, early behavior that can be compared to later behavior, so we're not forced to treat Discovery Day as page 1. This is also why the safe mode interruption doesn't kill the story. Space data isn't a perfect movie, it's a forensic record. Analysts can combine the dedicated January run with earlier detections and then cross-check with other spacecraft that saw the same visitor from very different vantage points. For example, NASA has described Parker Solar Probe observations of 3I Atlas from October 18th to November 5th, 2025, using an imager that took multiple images per day. Different geometry, different instrument, same object. That's exactly how you pressure test conclusions. Meanwhile, the support layer around the data keeps getting better. Alongside raw archive access, the science support teams released Comet-centered products, background-corrected image time series, and photometric time series, so researchers don't have to reinvent every processing step from scratch. That doesn't replace independent work. It accelerates it, and it makes comparisons between teams much easier because everyone can start closer to the same baseline. So, what should we learn from this? Interstellar objects don't give second chances. The special part isn't hype, it's urgency. When a visitor like this appears, the smartest strategy is fast, transparent measurement. Capture a long baseline, publish the frames, and let the best ideas win. That's how a faint streak becomes a shared experiment. Next, teams will hunt repeating peaks in the light curve, test whether dust activity masks the nucleus, and compare models against the clean time series. If independent groups converge on one period, confidence jumps. If not, the puzzle stays open, and that's still a result. So the real headline isn't just a comet was observed, it's that a rare visitor forced a creative pivot, produced a time series strong enough to chase rotation clues, and then got released in a way that invites public cross-examination. That's a modern recipe for fast astronomy: long observations, careful processing, and verification by many eyes. Now, we'd love to hear from you. What do you think would be the strongest proof that we've truly pinned down 3I Atlas's spin? Share your thoughts in the comments. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. Your support truly makes a difference and helps this channel grow.